In 1906, Robert Milikan was able to determine the value of the charge on the electron in his oil drop experiment. A schematic of his experiment is shown here. It has an X-ray source placed over here and a high DC voltage source over here capable of providing potential difference ranging up to 10,000 volts. Over here is an atomizer for spraying oil into tiny droplets and a telescope over here to view the oil drop. Now let us see what we have inside this container. There are two plates over here. The oil is sprayed on the top like this. The top plate has a small hole over here. This hole allows the oil drop to enter this region between the two plates. The top plate is connected to the positive terminal of the battery. The X-ray comes from here and ionizes the gas that is present over here, which in turn charges the oil drop that enter in this region. Now at first the voltage is turned off between the plates. We watch the motion of the falling drop. First it accelerates because of the gravitational force Fg, and then due to viscous force Fv, a steady velocity is reached due to the air inside, which acts in a direction opposite to the motion of the oil drop. Let this velocity be v1. v1 can be known by recording the time required for an oil drop to fall a certain distance with a constant velocity. Let us see what forces act on the oil drop. While calculating the gravitational force, we have to take into consideration the buoyant force. Now Fg, which is the gravitational force, which is equal to 4/3 pi r cube rho minus rho air into g, where 4/3 pi r cube is the volume of the oil drop and g is the acceleration due to gravity. Rho is the density of oil and rho air is the density of air. Using Stokes' law, Fv equal to 6 pi eta r v1, where r equal to radius of oil drop and eta equal to viscosity of air. When the oil drop fall with constant velocity, then there should be no force acting on it. So these two forces are equal to each other. That is 4/3 pi r cube rho minus rho air into g equal to 6 pi eta r v1, or r square equal to 9 eta v1 divided by 2g rho minus rho air. Thus r is calculated if v1 is known, and accordingly Fg can be calculated from this equation. Now the voltage is applied between the two plates. The top plate is connected to the positive terminal, and force due to electrical field, which is Fe equal to Q into E, on the oil drop act upwards, where Q is the charge on the oil drop and E is the magnitude of electrical field. This force can do two things. Number one, it may stop the motion of the oil drop. In that case, Fg equal to Fe equal to Q into E. Now E equal to V divided by D, where V is the voltage applied across the plates and D is the distance of separation between the plates. This implies Q equal to Fg into D divided by V. All the quantities over here are known, so Q can be calculated. Number 2. The oil drop may rise up with constant velocity v2, which may be experimentally calculated by recording the time required for the oil drop to rise a certain distance. Now the viscous force acts downward because the oil drop is moving up. Now since the oil drop is rising up with constant velocity, all the forces acting on the oil drop should balance each other. That is Fe equal to Fg plus Fv, where Fv equal to 6 pi eta r v2 and Fg is 6 pi eta r v1. Therefore Q into V by D equal to 6 pi eta r v1 plus 6 pi eta r v2, which implies Q equal to 6 pi eta r v1 plus v2 into D divided by V. So in either case Q can be calculated. The charge on different oil drops was calculated. Now Milikan prepared a chart like this. The chart showed the charges he got on the oil drops, and he found the difference between two charges like this. It was noted that the charge on an oil drop is always an integral multiple of a minimum charge, and the minimum charge was found to be 1.602 into 10 to the power minus 19 coulomb. Actually, the charge was considered to be due to electrons being attached to the oil drop. So this minimum charge difference between two oil drops was taken as the charge of an electron, which was found to be 1.602 into 10 to the power minus 19 coulomb. We already know the charge to mass ratio of an electron in the experiment of J.J. Thomson with cathode ray tube. The ratio was 1.76 into 10 to the power 11 coulombs per kg. From this, m equal to charge of an electron divided by charge to mass ratio, which is equal to 1.602 into 10 to the power minus 19 divided by 1.76 into 10 to the power 11, which is equal to 9.1 into 10 to the power minus 31 kg, which is the mass of an electron.